Hello guys, so today I'll be explaining the chapter 2 notes, only the questions because I did a video previously explaining chapter 2. Chapter 2 is about solubility, okay? It's a very nice chapter. It's very simple compared to the previous ones before. So let's start. CQD number 1. Propose 2 heat methods for increasing the rate at which salt dissolves in water. Okay, I will give you the 2 methods, then I will add an extra information, okay? We have heating is the first method, and the second method is increasing the surface area. If you increase the surface area, what happens? Crystals become smaller. Okay, now these are 2 factors which increase the rate at which salt dissolves in water. But let's take it like this. Let's take it in, we have a glass over here, and inside the glass we have water. Okay, now what's dissolved in the water? We have some salts. Let's say the red is the salt dissolved in water. Let's say it is a saturated solution. What does this mean? This means if you add any more salt, it will not dissolve. So let's say we added salt that's like this big. Okay, we put it will not dissolve. It will just like stay over here, whereas the other ones, the smaller pieces, will have dissolved. Now, if you increase the temperature, so let's say we added fire. This is fire. Sorry for bad drawing. You added fire or heat. Okay, then what happens? This over here is more likely to dissolve. Okay, it's way more likely to dissolve. Also, if you took this and you made it into smaller pieces, you broke it into 1, 2, 3, 4, like you made it really small pieces, so you increase the surface area, then it is what? It is more likely to dissolve. So that means what? If this solution is saturated, but then we increase the heat and we increase the surface area, then what happens? That means we are changing its saturation, we're changing its solubility. So, in summary, if you increase the heat or increase the surface area, it will increase the rate at which a salt dissolves in water, so it will make the dissolving faster, and it will also increase the saturation or increase its solubility. That's CQD number 1 finished. CQD number 2 is very important. It's a graph. Okay, we have to pay attention to this graph, okay? So let's start. What is the solubility of potassium nitrate at 20 degrees Celsius? Okay, when we're talking about solubility, okay, this means what? This means the mass of something over, not the mass of something, the mass of the solute over the mass of solvent. Solute is the thing that dissolves, and solvent is the thing that it dissolves inside. So the universal solvent is what? The universal solvent is water. So whenever they're talking about solubility, they're talking of the mass of solute over the mass of solvent. So let's go up. We need the solubility of potassium nitrate at 20 degrees Celsius. So let's go. Here's our temperature, 20 degrees Celsius. We're going to take it to the potassium nitrate curve, and we find that it is almost 30 grams. But this is what? This is the mass of the solute. We said the rule for solubility is solute over solvent. So they told us the mass of solvent is what? 100 grams. So 100 grams of the solvent, which is water. So the solubility of potassium nitrate at 20 degrees Celsius is 30 grams of potassium nitrate over 100 grams of water. Okay, now at 50 degrees Celsius, let's do the very same thing. We go from 50 to the, from 50 we're gonna go to the potassium nitrate curve, then we're gonna draw it like this. It is almost what? 80 grams, but this is the mass of the solute, and we know solubility is solute over solvent. We know that the mass is 100 grams of water, so the solvent is then water. So that means the solubility of potassium nitrate at 50 degrees Celsius is 80 grams per 100 grams of water. Okay? Now part B. By how much will the solubility of potassium nitrate increase if the temperature is increased from 20 degrees Celsius to 50 degrees Celsius. Very simply, you take final temperature, which is 50 degrees Celsius, you find its solubility, and you subtract it from the initial temperature solubility. So what's the final temperature solubility? We got it in the last one. This was 80 gram per 100 gram. This one was 30 gram per 100 gram. Okay, so we're gonna do the solubility of the final temperature, so 80 over 100, minus the solubility of the initial temperature, so 30 over 100. If you subtract, you can do it on your calculator, it becomes 50 over 100. But please don't do like math and put it in simplest form, just keep it 50 over 100 grams, okay? So part B is 50 over 100 grams. Now, what mass of potassium nitrate forms if a saturated solution in 100 grams of water is cooled from 40 degrees to 10 degrees? Very simply, we are gonna take temperature final, this is temperature final, and temperature initial. We're gonna find the solubility of temperature final and the solubility of temperature initial, okay, of potassium nitrate at these temperatures. So we have 40 degrees Celsius and 10 degrees Celsius. At 40 degrees Celsius, I believe it's this one, go up, you will get that it is approximately 60. So for 40 degrees Celsius, it's approximately 60 grams per 100 grams of water. And then at 10 degrees Celsius, wait, where's the curve? Curve is over here. If you do it, you will get that it's almost 20. My bad. So at 10 degrees Celsius, it is 20 grams per 100 grams of water. So now they told us, please keep these in mind, 60 grams and 20 grams. So if we go down, they told us what they're telling us. What mass forms if a saturated solution in 100 grams of water is cooled from 40 degrees to 10 degrees Celsius? So very simply, you're going to take temperature final, which is 10, you're going to put its solubility, which is 20 over 100, and then you're going to subtract it from what? From the temperature initial, which was 40 degrees Celsius. Its solubility was 60 over 100, and you will get negative 40 over 100. So 40 grams over 100 grams of water. My question is, can the grams ever be negative? Can mass ever be negative? No. So you're gonna do temperature final minus temperature initial. You're gonna do solubility of temperature final minus solubility of temperature initial. You're gonna get a negative number. If you get a negative number, okay, like in this case, you're gonna exclude it. You're gonna remove the minus, and you're gonna say that since it cooled down is instead of the minus, since it cooled down from 40 degrees to 10 degrees, its solubility became what? 40 grams over 100 grams of water. So now this is the first part of part C done. Now for the second part, we have from 60 degrees Celsius to 20 degrees Celsius. So let's go up. 60 degrees Celsius is what? What's the temperature? Sorry, what is the mass dissolved? If you go up, it is almost, I will say 105. So let's say at 60 degrees Celsius, okay. Wait, sorry, excuse me. Let me redo it because it wasn't that clear. Okay, actually it's not 105, it is, I'll say 102. Okay, this is an estimation from my side. I'm not sure what the actual what the actual mass is. So we're gonna say that at 60 degrees Celsius, the mass was 102 grams per 100 grams of water. Okay? Then at 20 degrees Celsius, if you remember from the first question, we got it to be 30 grams per 100 grams of water. So please keep these two values in mind. Let's go down. They're telling us if the water is cooled from 60 degrees Celsius to 20 degrees Celsius, so temperature final, temperature initial, we're gonna do the solubility of temperature final minus the solubility of temperature initial. Solubility of temperature final was 30 grams over 100 grams of water minus temperature initial, which was 102 grams over 100 grams of water. Now again, if you check the CQD and I have a different answer, it's because of the estimation. I probably estimated differently than how the answers estimated it, okay? So if you do on your calculator 30 over 100 minus 102 over 100, you are gonna get minus 72 grams over 100 grams. And then we go back to the same issue as the first time. We have minus, but can mass ever be negative? That's not a thing, so we're gonna cancel the minus, we're gonna forget about it, and we're gonna state our reason. We're gonna say since the temperature cooled down from 60 degrees Celsius to 20 degrees Celsius, the solubility becomes, or the mass becomes 74, or not 74, my bad, 72 grams over 100 grams. Now, another thing that I didn't pay attention to was that in part A, they asked us for the solubility. When they ask you for the solubility, you do solute over solvent. But in part C, they asked us for the mass. So this is a mistake from me. That's why I'm going to correct my mistake now. When they ask you for the mass, you only put the mass of the solute that you found. So I believe for the 40 to 10 degrees, it was 40 grams, if I'm not mistaken. So now the mass of potassium formed will be 40 grams. And from 60 to 20 degrees, we got 72. So it's going to be 72 grams. So please pay attention to this and don't do any mistakes like me, okay? Now, what mass of water is needed to dissolve 50 grams of potassium nitrate at 40 degrees Celsius? This question is really nice, okay? So we need to dissolve what? 50 grams of potassium nitrate. So we're gonna put it like this. 50 grams of potassium nitrate over the mass of water, okay? This is the solubility for the 50 grams. They're telling us at what? At 40 degrees Celsius. So it's equal to what? If you remember, we got that the solubility at 40 degrees Celsius from the graph was what? 60 grams over 100 grams. So we need to find the mass of water to dissolve 50 grams of potassium nitrate at 40 degrees Celsius. We have at 100 grams of water, the mass of potassium nitrate dissolved at 40 degrees is 60 grams. So very simply, you can do cross multiplication. So then it becomes 100 times 50 over 60. So if you do it on your calculator, you are gonna get 83.333. So this is the mass of water needed to dissolve 50 grams of potassium nitrate at 40 degrees Celsius. So now, again, we have a question. What mass of potassium sulfate will dissolve in 2 kg of water at 20 degrees Celsius? What was the solubility at 20 degrees Celsius? At 20 degrees Celsius, I believe it was... but look, before we remember, here they asked us potassium nitrate, but here they're asking us what? They're asking us potassium sulfate. So we're gonna stop everything, because we read and we didn't do any mistakes like Amanda, okay? We're gonna go at 20 degrees Celsius, we're gonna find the mass or the solubility of potassium sulfate. So it is 10 grams per 100 grams of water. So if we go down again, we have the solubility at 20 degrees Celsius of potassium sulfate is 10 grams over 100 grams of water. Okay, now we have what? We have the mass of water. So what we're going to do, we're going to form an equation. The mass of potassium sulfate of KSO3. You don't have to write it like this. You can write potassium sulfate, but I'm just putting it in its form, you know? So the mass of KSO3, potassium sulfate, over the mass of water, which was 2 kg, is equal to 10 grams over 100 grams. If you notice, we have what? Two different units. We have kilograms, grams, and grams. So definitely we need to change them so they are all the same unit. So let's change this from kilograms to grams. It becomes what? 2,000 grams. So now by doing cross multiplication, you will get 2,000 times 10 divided by 100. Okay, if you do it on your calculator, you are gonna get 200. So the mass of potassium sulfate that will dissolve in 2 kg of water at 20 degrees Celsius is what? Is 200 grams. So I believe that was CQD number 2. Now we have CQD number 3. This is very, very important. Okay, we have something I explained in the video that I will tag in the comments. We have molecular compounds and ionic compounds. We have some molecular compounds, some which are like very few of them, that will form electricity in water, or ions, which are not pure ions in water. And then we have the ionic, which form pure ions in water. Then we have the regular molecular compounds, which do not form ions in water. So let's start. Okay? So CQD number 3. Glucose, its equation is C6H12O6. It is a molecular compound. So looking at glucose, you cannot form it into ions. It's a very big, very complex compound. So you cannot form it into ions. Even though it dissolves in water, it does not form ions. So it will stay the exact same. But the only difference, so it's C6H12O6, but the only difference is since that it dissolved, it becomes aqueous. Okay? For the second part, we have NaCl solid. NaCl is an ionic solid, so it dissolves and forms ions. What are these ions? We have Na plus, and it is aqueous since it's dissolved in water. Okay? Plus Cl minus, and it is aqueous. So now HCl gas is a molecular ion, a molecular compound, sorry, but even though it is a molecular compound, since it dissolves in water, okay, it is a very rare exception. You have to remember that HCl, when it dissolves in water, it gives us what? It gives us H plus, but it's aqueous, okay, plus Cl minus, and it is aqueous. So then later on in the chapter, you will learn about the table of solubility that you have to memorize. It came so many times in the AMS, so it's really important to memorize, okay? So the table is extremely, extremely important to memorize. So we finished CQD number 3, on to CQD number 7. Let us classify the salts as soluble or slightly soluble. If you wrote the table in front of you or you have it memorized, this is gonna be really easy for you guys. But anyways, all salts containing nitrates, anything containing a nitrate is soluble because nitrates dissolve with everything. All salts of alkali, metal ions, alkali which are like N+, K+, Li+, etc. Okay? It is dissolvable with everything, so we say it is soluble. Group 2 metal carbonates. So of course they will give you like a periodic table in the exam. I'll open one right now. So this is the periodic table, okay? So let's say we have these over here, okay? We know they are group 2, so this is group 1 over here, then this is group 2. Group 2 meaning Be, Mg, Ca, Sr, Ba, and Ra. And carbonate is what? CO3. Actually, its ion is CO3 2 minus. So according to your memorizing, you will know that anything that is Be, Mg, Ca, Sr, Ba, and Ra, or anything other than NH4 plus, the alkali metals, or H plus, anything other than these is insoluble with CO3 2 minus. So that means if we're talking about these and it doesn't contain any of these, then definitely it is insoluble, or it has a low solubility with the CO3 2 minus, which is carbonate. So again, we will come here and then we will classify this as slightly soluble. Now, chlorides of silver and lead. Okay, lead is Pb2 plus, silver is Ag plus. Okay, we know chlorides is Cl minus. And if you remember from the table you wrote or from the table you memorized or whatever, you will know that Cl minus is insoluble with Pb2 plus and Ag plus. So it will form a white precipitate. So we say this over here is what? Slightly soluble. Okay, now CQD number 4. So CQD number 4, we have A, B, C, and D. We need to state what will be observed, the name of the precipitate, and we need to write a net ionic equation of the reaction occurring. So we have BaNO, this is N, BaNO32, okay, plus Na2SO4. Very first thing you're gonna do is that you're gonna separate them into what? Into their ions. So if you're gonna separate them into your ions, you're gonna get Ba2 plus, you're gonna get NO3 minus, you're gonna get Na plus and SO4 minus. Then what you're gonna do is that you're gonna switch every cation means positive, with the other anion. Anion means negative. So Ba2 plus, its original anion was NO3 minus, so it will take the other one, which is SO4 minus. Then Na plus, its original anion was SO4 minus, so it will take the other one, which is NO3 minus. So now we have what? We have two compounds formed, which are Ba2 plus SO4 minus will form what? Will form BaSO4, okay? And then we have Na plus NO3 minus will give us what? NaNO3. We know anything that is in the reaction with NO3 minus is soluble, so its state is aqueous, okay? Whereas here, BaSO4, we know SO4 minus does not dissolve with everything, so it is insoluble with a lot of cations, including Ba2 plus. So since it's insoluble, it will form a precipitate, which is Ba2SO4. We say it's a solid. And what is the color? The color will become white, or the color of this precipitate is white. So for the first one, we stated everything. Now for the second one, we have AgNO3, okay, plus NaCl. First step we're gonna do, we're gonna separate them into their ions. Okay, Ag becomes Ag plus, NO3 becomes NO3 minus, Na plus and Cl minus. Then as we did before, we're gonna switch every cation with another anion. And so now what do we get? We get two things, which are Ag plus Cl minus will give us AgCl, okay? And then Na plus NO3 minus will give us what? It will give us NaNO3, okay? So also don't forget that if you're having anions and cations, don't forget to put aqueous next to them, okay? So definitely anything that will react with NO3 minus is soluble, so it will be aqueous. And then Cl minus, if it reacts with Ag plus, it will form a precipitate. This you know it from the table of solubility. So it will form a precipitate and its color is white, so it will form a white precipitate. That's part B. We finished part B. Now part C, we have BaNO3, 2, plus NaCl. Again, we're going to divide them into their ions. Okay, we have, for example, Ba2 plus and O3 minus, and then we have Na plus and Cl minus. So as we did before, we're gonna bring each one to the other. Okay, sorry, I keep on moving my tablet. So we are gonna get Ba2 plus reacts with Cl minus to form BaCl2. Then we have Na plus reacts with NO3 minus to give us NaNO3. But don't forget, of course, to put the aqueous here, 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 and here. Okay? Now, from the table, like from the solubility table, we will know that Cl is soluble with Pa2+, so we're gonna put it as a solid. And anything that reacts with NO3-, any cation that reacts with NO3- is, my bad, here this is soluble, so we put it aqueous. Please, that was a mistake from me, sorry. Okay? So then, any cation that reacts with NO3- will also be soluble, so it is also aqueous. So if you notice, we have here aqueous and here aqueous, so we don't have a precipitate. So here we say no precipitate formed. Okay? So that was it for part C, which is BaNO32 and NaCl. Now we go on to part D. Part D, we have CaNO3 2 plus Na2 CO3. Okay, so let's break them into their ions. We have Ca2 plus, NO3 minus, Na plus, and CO3 2 minus. So as we did before, we're gonna switch the cations and anions. So now we get Ca2 plus aqueous will react with CO3 2 minus aqueous to produce what? To produce CaCO3. Okay, then we have Na plus aqueous react with NO3 minus aqueous to produce NaNO3. Now anything that reacts with NO3 is soluble, so this is going to be aqueous. But here, if you remember, we said CO3 2 minus reacts with only a specific number of elements, a specific number of ions. And Ca2 plus is not one of those ions, so they're going to form a precipitate. So we're going to put solid, and the precipitate color is what? So that's it for question number 4. Now CQD number 5. Okay, so a solution is known to contain PbNO3 and MgNO3. We know anything that reacts with NO3 is soluble, so this, it's aqueous, and this is aqueous. Okay, it's required to remove the lead-2 ions. We need to remove the Pb2 plus ions from the solution without removing magnesium ions. So we have to keep the Mg2 plus ions. So how could we possibly do that? Very simply. We know that what if you react it with the Pb2 plus will form a precipitate. The only thing we know that reacts with Pb2 plus to form a precipitate is Cl. Cl minus. So Cl minus, it reacts with Pb2 plus, okay, it forms what? A white precipitate, okay? But however, if Cl minus reacts with Mg2 plus, does it form a precipitate or it's soluble? It's soluble. So this is exactly the case that we need. Okay, so by looking, NaCl is the only thing that has what? The only thing that has Cl ions. So we're gonna choose A because we are gonna have a solid which is PbCl2, okay, and then something soluble, something aqueous, which is MgCl2. And since it is soluble and this is insoluble, we can filter it, okay? So we do the filtration. This is the filter, okay? Looks something like this. You do the filtration. Here you have the cup. Here what comes out is the aqueous, which is the MgCl2, and what remains in the top is the precipitate or the solid, which is PbCl2. So that's CQD number 5 done. Now CQD number 6. What would be the weight of the precipitate formed when 100 milliliters of 0.500 molarity NaCl is added to 50 milliliters of 0.100 molarity AgNO3? First things first, we're gonna take NaCl, okay, and then AgNO3. We're gonna form precipitate for we're gonna take the ions of AgNO3 and NaCl. Ions of AgNO3 become Ag plus, NO3 minus. The ions of NaCl become Na plus and Cl minus. So if you notice, you don't need to balance everything, they're already balanced. So in AgNO3 it's already balanced, and in Na plus and Cl minus, in NaCl it is also balanced. So very simply, we can find the number of moles. To find the number of moles, which I will denote as N, so the number of moles of AgNO3, it is what? It is the molarity multiplied by what? Multiplied by the volume in liters. So molarity means concentration, so let's denote it as C. So the molarity or concentration C multiplied by the volume in liters, okay? So to change 100 milliliters to liter, we're gonna divide by 1,000, we get 0.1 liter, and then here we get 0.05 liters, okay? So now to find the number of moles, we're gonna do 0.1 times 0.5. So the number of moles of NaCl is 0.05 mole. Okay? Then the number of moles of AgNO3 is 0.05 times 0.1. We're gonna get 5 times 10 to the negative 3. So the number of moles of AgNO3 is 5 times 10 to the negative 3. So since it's already balanced, okay, 1 AgNO3 will give us how many moles? Will give us 5 times 10 to the negative 3. So 1 Ag plus will also give us 5 times 10 to the negative 3. 1 NO3 minus will also give us 5 times 10 to the negative 3. Here 1 NaCl gave us 0.05 mole. So 1 Na plus will give us 0.05 mole, and 1 Cl minus will give us 0.05 mole. So now we found what? We found the moles of every single ion. So now let's find out which of them forms a precipitate. We're gonna take here this negative, and we're gonna take here this negative. So it becomes Na plus NO3 minus. Of course, add the aqueous. I'm not gonna add it because I have cramped space. So NaNO3. Okay, this is 3. And then we have Ag plus Cl minus gives us AgCl. We know NaNO3 is aqueous, and we know also that AgCl is a precipitate, it's solid. So they're asking us for what? They're asking us for the weight of the precipitate form. So now, okay, I'm gonna erase all of this and I'm gonna write on the side Ag plus, its number of moles is 5 times 10 to the negative 3, okay, and then Cl minus, its number of moles is 0.05 mole. Now we're going to take the ionic equation of the precipitate, which is Ag plus aqueous plus Cl minus aqueous will give us what? Will give us AgCl solid precipitate. Now here, this is a very important step. If you remember, we got that the number of moles of AgNO3 was 5 times 10 to the negative 3. And then the number of moles of NaCl was 0.05 mole. So definitely, by looking at it, which one is the limiting reagent? Which one has a smaller number of moles? It is the AgNO3. Anyways, by looking at Ag plus and Cl minus, which of them is the limiting ion? It's Ag plus. So we will be using the limiting reagent. We will be using the number of moles of the one that has the less number of moles. So the limiting reagent, or the limiting ion, which is Ag plus, its number of moles is 5 times 10 to the negative 3. Okay, so if 1 Ag plus is 5 times 10 to the negative 3, that means 1 AgCl, its number of moles will be 5 times 10 to the negative 3. So very simply, to find the mass or the weight of the precipitate form, which is AgCl, we're going to multiply the molar mass of AgCl, which you can get it from the internet, but it is 143.5. We multiply it by 5 times 10 to the negative 3, and we will get 0.7175. So this, of course, is in grams. So this is then the weight of the precipitate form when 100 milliliters of 0.500 molarity NaCl is added to 50 milliliters of 0.100 molarity AgNO3. Now we have the tests over here, very important to memorize them, and we go all the way to CQD number 8. By memorizing it, okay, we will just scan through it quickly. They told us they put 4 different potassium halides. Then they added silver nitrate, which is AgNO3. The halides are what? The halides are, or the potassium halides to be exact, okay? They are what? They are K, because K is potassium. Then we have Ki, okay? Then Kf, then KCl, and then KBr. You're saying, Amanda, how did you get it? Potassium is K. And remember, the halides are IFClBr. I minus, F minus, Cl minus, and Br minus. One note, F does not react with anything, okay? So it doesn't react with K, and it will not react with anything, okay? So anytime you add Ag to I, Cl, or Br, this is something we memorized from the tests. We know that I will produce a yellow precipitate. F will not react, of course, so no change. Cl will produce a white precipitate, and Br will produce a creamy precipitate. So if we're going to put it in order, we know the formation of a yellow precipitate has I, so it's Ki. Of a white precipitate that turns violet, then black when exposed to light, is KCl. And then formation of creamy precipitate is KBr. No change is KF. So that is CQD number 8. CQD number 9. Okay, so you guys have to memorize the flame test. Okay, we know that the cation that gives us a yellow-orange flame is Na+. Okay, the cation that gives us a lilac-violet flame is K+. Crimson red is Li+. Blue-green is Cu+. Pale green is Ba+, and brick red is Ca+, Ca2+, Ba2+, and Cu2+, I believe. So remember, yellow, orange, Na+, lilac, violet, K+, crimson red, Li+, blue green is Cu2+, pale green is Ba2+, and brick red is Ca2+. Now we have CQD number 10. Also, you have to memorize these, okay? They gave us some ions over here, Cr3+, blah, blah, blah. And we need to fill in the blank. Whenever you see reddish-brown precipitate that does not dissolve with excess base, okay, sodium hydroxide means NaOH, so it does not dissolve with excess NaOH, it is always Fe3+. A dirty green precipitate is Fe2+. Blue precipitate is Cu2+. White precipitate, okay, we have many things that have a white precipitate. A white precipitate, it forms a white precipitate with sodium hydroxide, but then no reaction or no precipitate with ammonia. This is Ca2+. If it forms a white precipitate with ammonia and does not redissolve in excess ammonia, this is Al3+. If it forms a white precipitate with NaOH and it redissolves in excess ammonia, so it also forms a white precipitate but redissolves in excess ammonia, this is Zn2+. And then finally, a green precipitate that dissolves in excess sodium hydroxide is Cr2+. So that's CQD number 10, done. CQD number 11. Okay, they gave us some cations, Ag+, Ca2+, Na+, Zn2+, and Ba2+. Which of the following given ions forms a white precipitate upon addition of an aqueous solution of K2SO4? So they're asking us which of the following, okay, will not react, will not dissolve, okay, is not soluble with K2SO4. Definitely, since we have all of them are cations, we're going to be looking at the anion. What's the anion here? It's SO4 2-. So which of the following does not dissolve with SO4 2-? It's very simply Ca2+ and Ba2+. Then, which of them does not dissolve with Cl-? We know very well it's Ag+, and it forms a white precipitate with Cl-. Then we have Br-, and it forms a creamy precipitate. So very simply, it is Ag+. Basically, all of this chapter is memorizing. So now CQD number 12. So after CQD number 12, we will have the top questions. Let us know the characteristics of each gas. It turns lime water milky. Lime water milky, what turns it? It is carbon dioxide. So which releases carbon dioxide? CO3 2-. pungent smelling gas that turns red litmus paper blue. So when we're talking about NH4 plus and NO3 minus, they release the same gas. But if we're talking about NH4 minus and it reacts with a base and it releases a pungent smell, then we're talking about the ammonia gas NH3 released from NH4 plus. So NH4 plus. Then again, they told us it releases a gas that turns moist red litmus paper blue. Whenever you see heated with aluminium and red litmus paper blue, no, it is the ammonia gas NH3 released from NO3 minus. Now, which of the given ions releases a gas with a choking odor upon the addition of an acid? Choking odor is always sulfur dioxide, SO2. Or, however, if it turns the red litmus paper into bleach, then this is chlorine gas. Chlorine. Okay, but here chlorine gas is not given as one of the options. So if it releases a choking odor, okay, upon the addition of an acid, then this is what it is, SO2 gas. What releases SO2 gas? It is SO3 2 minus. So that's CQD number 12 done. Now we have still some one top question, and then we have the past papers. Okay, they added the past papers for us, so it's really convenient. So I'm going to zoom out and go to CQD number 16 top. So, many insoluble salts can be prepared by precipitation reaction between soluble salts. All potassium salts and all nitrate salts are soluble. Okay. So now in part A, a student adds a potassium sulfate, K2SO4, to a barium nitrate, BaNO3, to solution. A white precipitate is formed. They need the chemical formula of the white precipitate. They gave us a hint directly that all potassium salts and all nitrate salts are soluble. So that means potassium, which is K, and nitrate, which is NO3, directly soluble. So they will not form a precipitate. So we're going to remove the K and we're going to remove the NO3. So what's left for us? We're left with SO4 2 minus ion plus Ba2 plus ion. So it will form which precipitate? It will form the precipitate BaSO4. Now it's a white precipitate, so BaSO4 solid precipitate. Now they need us to write the chemical equation for the reaction between potassium sulfate and barium nitrate. Very simply, you can do K2SO4 plus BaNO3 will release. Also, don't forget to put aqueous because they were both soluble before. So aqueous will release what? Will release KNO3. How did we get it? We mixed the ions. We switched the ions. And this is aqueous since it's soluble plus BaSO4, which is a white solid precipitate. So this is the chemical equation for the reaction. Now, part B. We have K2CO3 and AgNO3. Question. They told us that K2CO3, they told us that potassium salts and nitrate salts are soluble. Why is that? It's because K plus is soluble with everything and NO3 minus is soluble with everything. So if we make their ions, it's going to be K plus, CO3 2 minus, and then Ag plus, and then NO3 minus. Okay? We know K plus and NO3 minus are soluble with each other. So they will form what? They will form KNO3, which is aqueous, okay, plus Ag 2CO3, which is what? Which is a precipitate solid. Okay, so our precipitate solid is Ag2CO3 because we know CO3 2 minus does not dissolve with. So the chemical formula of the white precipitate Ag2CO3 is basically Ag2CO3. Okay, and then we put solid. Alright, now the net ionic equation, this is different. Net ionic equation are only the ions that reacted. So we remember, we took Ag plus, it reacted to form with the, CO3 2 minus to form what? To form Ag2CO3 solid. Net ionic equation means all the ions that react to form the precipitate. Our precipitate is Ag2CO3. So it becomes Ag plus CO3 2 minus gives us Ag2CO3 solid. Is it balanced though? No, it's not, because we have 2 minus and we have only 1 plus. So to balance it, we're going to multiply the Ag by 2. So that is then part B done. Now part C. Barium nitrate solution produces a white precipitate with both carbonate ions and sulfate ions. Why? Acidified barium nitrate solution is used to distinguish between carbonate ions and sulfate ion. Very simply, this is something very easily. We know sulfate ions release what? Is SO4 2 minus. And, okay, I'm gonna cut that out. So very simply, we need to know that sulfate ions are SO4 2 minus, carbonate ions are CO3 2 minus. We know carbonate ions release what? They release CO2 gas. So when acidified barium nitrate reacts with these chemicals, the nitrate will remove the carbonate by releasing carbon dioxide gas. So how do we distinguish between carbonate and sulfate ions? You can do a test by putting lime water, and if the lime water turns milky, okay, then you know CO2 gas is released. That means we have put carbonate ions with barium nitrate. So that's pretty much it for part C. Now we have the past papers. So now let's solve the past papers. Solid Q and solid R were analyzed. Solid Q was zinc carbonate. Tests were done. Okay, the tests on solid Q. Zinc carbonate is what? ZnCO3. So, part A, solid Q was placed in a boiling tube. About 10 centimeter cubed of dilute sulfuric acid was added to the boiling tube. Any gas produced was tested. Okay, since we're adding sulfuric acid and in zinc carbonate, solid Q, we have carbonate, which is CO3 2 minus. When CO3 2 minus reacts with an acid, it produces carbon dioxide, which is CO2 gas. So we can say that because there is a gas produced, which is carbon dioxide, so we will say that there is going to be fizzing. Fizzing means bubbles. You see bubbles. Okay? This is the first thing you're gonna see. The second thing you're gonna see is a colorless solution. Colorless solution. And then finally, the last thing is because our gas is CO2, it's gonna turn lime water milky. So how to see? You see you have 3 points over here, so do 1, 2, 3. Okay, now identify the gas given off in A. It is carbon dioxide, which is CO2. Now part C, sorry. The reaction from A was filtered. The filtrate was solution S. Okay, so from A, we did a solution in solid Q. It was placed in a boiling tube. We had zinc carbonate. Carbonate will react with sulfuric acid, which is H2SO4, and then zinc carbonate was ZnCO3. So the H2 will react with the CO3 to produce what? To produce carbon dioxide gas. So that means if we go back in part A, they're telling us we have the filtrate of solution S is going to be definitely the liquid part. So again, what do we have? We have zinc CO3 plus H2SO4. We said the CO3 will go away with the H2 to form carbon dioxide. Then we have zinc with the SO4, okay? So the NSO4, they produced what? This is an insoluble solid, so they will produce a white precipitate. So now, they're telling us aqueous sodium hydroxide was added. So now they added what? Sodium hydroxide, which is NaOH. A base was added dropwise in excess solution S in the boiling tube. NaOH will form a white precipitate with Zn. So look, we have Zn, and if you remember, Zn2 plus, if you put it in NaOH, it will form a white precipitate that dissolves, this is a D, dissolves in excess NaOH, or in excess base. That's part I. Part II, explain why it's not possible to identify the cation obtained in solution S from your observations in CI. Well, if you remember, we have what? We have Zn2 plus and Al3 plus. You put them both in NaOH and they give you the very same result. So it's not possible to identify the cation obtained in solution S. Okay, because aluminium or Al3 plus gives the same result. Alright, part 3, suggest an additional test that can be done on solution S to confirm the cation was Zn2 plus. Basically, if you add NH3 ammonia, if you add it plus to the Zn2 plus, okay, you will get what? You will get white precipitate that dissolves in excess ammonia, okay? Whereas if you added Al3 plus to the excess ammonia, it will form a white precipitate that's insoluble, that does not dissolve in excess ammonia. So very simply, just add ammonia and then it will produce a solution, because excess ammonia will dissolve the Zn2 plus. Now here we have the tests on solid R. We have a yellow flame. Yellow flame means Na plus. It's a sodium ion. And then in test 2, we have a yellow precipitate formed with what? With aqueous silver nitrate, which is AgNO3. So what anion added to AgNO3 will give us a yellow precipitate is I minus. So definitely the first one is Na plus, the second one is I minus. So solid R is NaI. And if you were to write it, it would be sodium iodide. So that's the first past paper done. Now the second one that we have is this one. Now we have solid I and solid J were analyzed. Tests were done on each substance, okay? Dilute hydrochloric acid was added to a tube containing solid I. So solid I was put into this tube. It reacted with hydrochloric acid, which is HCl. And then effervescence, meaning there is a gas formed. Okay, it formed a colorless solution and the gas termed lime water milky. Please memorize, anytime you see colorless solution and lime water milky, that means the gas released is carbon dioxide and the ion that released it is CO3 2 minus. A red flame. Red flame means lithium. Lithium is Li plus. Be careful if they tell you a brick red flame or a crimson red flame. Majority of the time, if they tell you a red flame, it means lithium. If it was Ca2 plus, they would tell you a brick red flame. So definitely it's lithium. And then the solid I is LiCO3. So part A is to identify the gas. It is CO2, carbon dioxide. The solid I is LiCO3. Okay, then now we're doing tests on solid J. Solid J was aluminium chloride. Aluminium chloride is AlCl3. Okay, so solid J was dissolved in water to form this. Okay, the first test, part C, sodium hydroxide and AOH was added to this. We know that the ions of this are what are Al3 plus and Cl minus. Adding NaOH to Al3 plus gives you a white precipitate that dissolves in excess NaOH. Now in the second one, we added ammonia, which is NH3. Adding ammonia to AlCl3, we know AlCl3 has the ions Al3 plus and Cl minus. So NH3, when it reacts with Al3 plus, it will form a white precipitate that doesn't, pay attention to, doesn't dissolve in excess ammonia. I'll write NH3. So that is part D and part C done. Then we have part E and part F. They told us that they added dilute nitric acid followed by barium nitrate. Barium nitrate is what? BaNO3 2. They added it to AlCl3. Now what are the observations? Definitely, let's divide them into their ions. We have Al3 plus and then plus Cl minus. Then we have the A2 plus plus NO3 Al3 minus. Then if we're gonna switch, so we give this one, we give Al3 NO3 minus, and then we give Cl minus Ba2 minus, we're gonna get Al3 plus NO3 minus gives us Al NO3 3, and then Ba2 plus Cl minus gives us BaCl2. If you look at your solubility rules or you memorize them already, you will know NO3 dissolves with everything and Cl2 will dissolve with everything except for Ag+, Bb2+, and Cu2+. So definitely these are both soluble solids. So that means our observations in part A are no change. Now finally they added what? AgNO3 to AlCl3. Again, let's divide them into their ions. We have Ag plus NO3 minus. Then we have Al3 plus Cl minus. We're gonna give this and give that. So now we get Ag plus Cl minus gives us AgCl, which is a precipitate, a white precipitate. And then we have Al3 plus NO3 minus gives us AlNO3 3, which is aqueous. So definitely we will see a white precipitate. And that is it for this past paper. Then we have past paper March 2021, page 62. So now let us see. We have two solids, solid C, solid D were analyzed. Let us see, these are the tests done in each solid. Now for solid C, we did a test, a flame test, and we saw a red flame. That means this could possibly be Li+. The cation is Li+. Then solid C was dissolved into distilled water to produce solution C. They added an AOH2 solution C. There was no change. So that means it's definitely none of the things that will react to form a precipitate with sodium hydroxide, which is an AOH. Then in test 2, what did they do? They put a piece of aluminium foil. It was added to the mixture. The mixture warmed gently and there was a gas produced while tested. Okay, what was seen? There was effervescence, definitely that means there's a gas, and it turned red, litmus paper blue. Turning red litmus paper blue means which gas? It means gas NH3, and since they didn't say there was a pungent smell, that means it is which gas? It is which ion? Sorry, it is NO3 minus. So now we have solid C. Solid C is LiNO3, and since NO3 dissolves with everything, so it's an aqueous solid. So we go down. The name of the gas that appeared in test 3 was ammonia or NH3. Solid C was definitely LiNO3, and we do not forget the aqueous. Or, to be honest, you can put it without the aqueous even. Okay, then part C. Now they're doing tests on solid D. Solid D was aluminium sulfate, meaning it is Al2SO4 and then 3. This is aluminium sulfate. They told us in part C they added sodium hydroxide and AOH. Let's put them into their ions. It is Al3 plus and SO42 minus. Adding NaOH to Al3 plus gives us a white precipitate that dissolves in excess NaOH. Okay, then part C, they added ammonia. Okay, they added ammonia, and again let's remember our ions. We have Al3 plus and SO42 minus. Adding ammonia to Al3 plus gives us a white precipitate that doesn't dissolve in excess ammonia, which is NH3. Then part E. They added silver nitrate, which is AgNO3. We know that it is Al3 plus ion plus SO42 minus AgNO3. Ag is Ag plus and then NO3 minus. So these are the ions of AgNO3. And if we're gonna switch their ions, we're gonna get what? We're gonna get AgSO4. No, actually Ag2SO4. Okay, plus AlNO3 3. So to be honest, they're both soluble, so they're both aqueous. That means there's gonna be no change. So over here, there is no change. Then finally, part F. They added barium nitrate, which is BaNO3. They added it to Al2SO4 3. By taking their ions, we have Ba2 plus NO3 minus. Actually, that means it's BaNO3 2. Okay? That means we have Ba2 plus and NO3 minus. Then we have Al3 plus and SO4 2 minus. And we're going to switch. Okay? We are going to get, now what we're going to get, BaSO4 plus AlNO3 3. BaSO4 is a white precipitate. So the observation we are going to see is a white precipitate. Okay, that was it for this past paper. Then now this one over here. Okay guys, so now we're going to be doing June 2023 paper 62. A student tests two substances, solution F and solid G. They're telling us they did these tests on solution F. They did a flame test and they got a light green color, or like a green color in the flame, pale green, light green, any of this means it is Ba2 plus. Okay, that means we have Ba2 plus ion. Effervescence was seen, that means the gas was released, and it turned red litmus paper blue. They didn't mention pungent smell. If they mentioned pungent smell, then the ion would be NH4 plus. But since they didn't mention pungent smell, then the ion is NO3 minus. So in part A, they're asking us describe how to do the flame test. What you're gonna do is that you're gonna get a wire, you're gonna clean the wire in acid, okay? Then until like you put it in the flame and it doesn't change the color of the flame. Then place the wire into the substance, okay, into the solution, and then place it into the flame. If it gives a light green color, then it's definitely Ba2 plus. So here we're gonna say step 1, clean platinum wire. Step 2, place in solution. And then step 3, check flame color. Alright, now part B, identify the gas given off in test 2. In test 2 there is effervescence, and we know it turned red litmus paper blue. If it turns red litmus paper blue, this means what? This means the gas released is NH3. And two things release NH3, ammonia gas NO3 minus and NH4 plus. But since they didn't mention a pungent smell, we're gonna exclude this and include the NO3 minus. So the gas given off was definitely ammonia, NH3, okay? And then the solution F was BaNO3 2. Or barium nitrate. So that's part C done. Part D, state what would be observed if the student adds dilute sulfuric acid to another portion of F. So we have Ba2 plus. Actually, first of all, we have the BaNO3 2, okay? And we added to it sulfuric acid. Its equation is H2SO4. So what happens? First of all, we're going to break it into their ions. We're going to get Ba2 plus, NO3 minus, H plus, and SO4 2 minus. Definitely, you will have this and this and this and this. So then you're going to have BaSO4, and it will be a white solid. It will form a white solid. So the observations is a white precipitate, because we found that BaSO4 will form a precipitate, and then HNO3 is soluble, so it won't do anything. So for part D, we have a white precipitate. So now, solid test on solid G, we have iron 2 carbonate. So I believe it is FeCO3. About 10 centimeters of dilute sulfuric acid is added to solid G. So they added what? They added sulfuric acid, which is H2SO4. We need to see the observation. Since we're adding an acid to FeCO3, let's take its ions. The ions are Fe2 plus and CO3 2 minus. If we're putting sulfuric acid or like any acid into this reaction and it will react with CO3 2 minus, it will release a gas. And to be more specific, this gas is CO2. So in chemistry, to observe the release of a gas, we will see bubbles. We call it effervescence or fizzing, okay? Or bubbling, whatever you want to call it. Okay, and then because carbon dioxide is released, we're gonna use a lime water solution, so it turns lime water milky. So that's E done. Now F. To the product from E, aqueous sodium hydroxide is added dropwise until in excess. So we're adding what? We have our ions, which are Fe2 plus and CO3 2 minus. We're adding an OH. Isn't that right? So if you remember, if you add NaOH to Fe2 plus, it will produce a dirty green precipitate that is insoluble. That is insoluble in excess NaOH. So very simply, by adding dropwise, like they're saying adding small drops, you will see a dirty green precipitate, and when you add excess, it doesn't dissolve. So that's the June 2023 paper 62. Now June 2023 paper 61. So here we have again solids E and solid F. This is how I think most of the exam will come, okay? So they're gonna do tests on solid E. Solutions form, steam is given off and condensation forms at the top of the tube. So what's released? H2O. Water is released. So that means it definitely contains water. Then if we go down, you will see that a brown precipitate forms, which remains when excess is added. That definitely means we have Fe3+, because if you remember, Fe3+ is a reddish brown precipitate. So if you see brown or if you see reddish brown, then it is Fe3+. Let's go down. Then they did a test that turns red litmus paper blue. That means which gas is released? NH3, ammonia gas is released. There is no change, okay, by adding silver nitrate, so it definitely doesn't contain Cl minus, Br minus, or I minus. And then, look, this is very important. They told us what? They told us that when they added barium nitrate, there was a white precipitate. So barium, Ba2+, forms only a white precipitate with SO4 2 minus. So that means this white precipitate is definitely SO4 2 minus. So I believe we have a couple of ions here. So let's go down and see. State what conclusions can be made about solid E from the observations in test 1. Since we found water, that means we can say it has or it contains water. Alright, the gas produced in test 3, if you remember, it turns red litmus paper blue, it is ammonia, so NH3. And if we go down, we have state what conclusion can be made about solid E from the test and observations 4. So if we go up, we see that there was no change after adding silver nitrate. And we said that means that it doesn't contain Cl minus, Br minus, or I minus. So definitely this is solid E. It doesn't contain Cl minus, Br minus, or I minus. Now based on the tests, we were able to identify 3 ions. If you go up, let's see the tests again. We have brown precipitate, so Fe3+. We have red litmus paper blue, so either NO3 minus or NH4+, but here we're going to take NH4+. Why? Because if you go up, you'll see that it was reacting in the beginning with a base, an AOH, and they warmed the product. So if you're reacting with a base and warming the product, then it turns red litmus paper blue and it releases NH3 gas, then the ion is NH4+. And then finally, a white precipitate by adding barium nitrate, we said that the ion was SO4 2 minus. So the 3 ions are Fe3 plus, SO4 2 minus, and NH4 plus. Now tests on solid F. Solid F is zinc sulfide. Zinc sulfide is ZnSO3. So its ions are what? Zn2 plus and SO3 2 minus. So first thing what happens is that they add aqueous ammonia, they add NH3. Remember, when we add NH3 to Zn2 plus, it forms a white precipitate if we add small drops, and if we add excess, it will dissolve. So it dissolves in excess. So remember, ammonia with the Zn2 plus will form a white precipitate that dissolves in excess. Now part F. To the second portion of solution F, the student adds a few drops of acidified aqueous potassium manganate. So we have what? We have, I believe, ZnCO3? No, ZnSO, sorry. We have ZnSO3, okay? And then we add what? Potassium manganate. So Zn2 plus SO3 2 minus. So definitely potassium manganate is gonna react with ZnSO3. Remember, anytime you see potassium manganate, okay, it will give you a purple pink color. So let's say purple pink color, okay? And but actually, what happens to this purple pink color after being added to a solution? It becomes colorless. So remember, anytime you add potassium manganate, it will give you a purple pink color, but then after a while it will become colorless. So purple pink color becomes colorless. Now part G. They added a nitric acid and barium nitrate, so BaNO3 2, and we have ZnCO3. Okay, so BaCO3, okay, plus ZnNO3 2. You're wondering, Amanda, how did you get this? Let's just divide them into their ions. We're gonna get Ba2 plus, NO3 minus, Zn2 plus, and CO3 2 minus. And we switched here with here, here with here, and so then we got these. Definitely by memorizing the solubility rules, you will know that this forms an aqueous solution, it's dissolvable in water, and this as well forms an aqueous solution, which is dissolvable in water. So since they're both aqueous, there becomes no change, okay? So now we have November 2022, paper 61. We have two substances, solid W and solid X, were analyzed. Solid W was zinc bromide. Zinc bromide is ZnBr2. If we break it into its ions, it becomes Zn2 plus Br minus. So what did they do? They added ammonia, NH3, to dropwise and then in excess, okay? Dropwise means like little dots, and then in excess means they put excess ammonia. So because it is reacting with zinc, what we're gonna say is that it will form a white precipitate at the beginning, okay? But because we're adding excess NH3, what happens? Zinc will dissolve in excess NH3. Now the second part, they added barium nitrate, which is BaNO3 2. They added it to zinc bromide. So let's break each one their ions. This one, its ions are Ba2 plus and NO3 minus. We already have the ions of this one. So if we're gonna switch them, we're gonna get Zn2 plus NO3 minus, okay? Will give us what? Will give us ZnNO3 2. And then we will have Ba2 plus Br minus. It will then give us Br2. Now they're both aqueous, they're both soluble. So that means if both of them are soluble, then there is no change in the observation. Then they added what? They added silver nitrate. So Ag NO3. And we know we have what? We have Zn2 plus and Br minus. Anytime you add AgNO3 to Br minus, it will form a creamy precipitate. So now let's go down. Now the tests on solid X. The acidified aqueous potassium manganate turned from purple to colorless. So remember, anytime we are dealing with a purple or potassium manganate turning from purple to colorless, that means we have the ion SO4 minus. Okay, they added silver nitrate, there was no change. Since they added AgNO3 and there's no change, so definitely there is no Br minus, no I minus, no Cl minus ions. Now for test 3, there was a white precipitate formed, okay, after adding barium nitrate. So this further proves that we have SO4 minus ions, okay. Then there is a green precipitate after adding an AOH. That means the ion is Fe2 plus. So in test 1, if we go back, they added that there was a gas released. Now what's the gas released? If you remember, we said that the ion was SO4 minus, and SO4 minus releases sulfur dioxide, SO2 gas. So SO4 minus releases SO2 gas. Okay, so the gas released was SO2. Now they're telling us to give a chemical test for water. Okay, there is something called anhydrous cobalt 2 chloride. Okay, this, it changes what? It changes from blue to pink in the presence of water. So remember, anhydrous cobalt 2 chloride, if you add water to it, it will change from blue to pink. So definitely solid X is FeSO4 or iron sulfate. So I believe this is it for paper 61 of November. Now the last and final past paper is June 2021, paper 62. So let us start. They used sodium hydroxide and it was added drop-wise. Sodium hydroxide is an AOH. They added drops and they found a white precipitate that does not dissolve in excess. So that means it can be either Al3 plus or Zn2 plus. Then they added silver nitrate. They added AgNO3 and we got a yellow precipitate. So that means we have I minus. Okay? So actually also I forgot, it can be Al3 plus or Zn2 plus or Ca2 plus, because all of them do not dissolve in a white precipitate if you add sodium hydroxide. They do not dissolve in excess. They form a white precipitate but they do not dissolve in excess, the three of them. So if we go down, it tells us that the mixture became brown and bubbled and the gas relit a glowing splint. Whenever you see relit a glowing splint, that means they released oxygen, O2. Now to be fair, here we were stuck on 3, Al3 plus, Zn2 plus, and Ca2 plus. If we think logically, since they didn't give us ammonia, okay, we're gonna cross these out because they didn't give us ammonia and they gave us only sodium hydroxide, so we will say that this is Ca2 plus ion. Now the gas produced in test 3 is O2 gas, okay, oxygen. Now, what is G? We said we have the ion Ca2 plus and I minus, so it is Cai2 or calcium iodide. And then if we go down now, they did what? Tests on solid H. Solid was hydrated copper 2 sulfate. Now these are stuff you have to remember. About half of solid H was placed in a boiling tube and heated up using a Bunsen burner. When you heat up the hydrated copper sulfate, what happens is that the solid, which was originally blue, okay, will become white. Okay, And then there will be some kind of condensation at the top of condensation at top of tube. Okay, so two observations. You can always know by the points how much they need. They need two observations. So a blue solid will turn white, and you will see condensation at the top of the tube. Now they said a flame test was carried out on solid H since we have copper Cu2 plus. Okay, the flame test for Cu2 plus will be a blue, or like dark blue, light blue, or blue-green, however you like to call it, a blue-green flame. So here we will just say blue or blue-green flame. Now they told us the remaining solid H was placed in a boiling tube. About 10 centimeter cubed of distilled water was added to the boiling tube. The tube was shaken to dissolve solid H and form solution H. Solution H was divided into two approximately equal portions in two test tubes. Okay, so remember we have what? We have hydrated copper sulfate. Okay, since we have Cu2 plus is one of the ions and SO42 minus is the other of the ions, and of course we added water. They did some experiments. Now let's see. They added ammonia. Okay, then they added an excess ammonia to Cu2 plus. What happens? It forms a light blue precipitate that will dissolve. So that dissolves in excess. Now, of course, when it dissolves in excess, it only dissolves in excess in ammonia. It will form a darker, I forgot how to write, a darker blue solution. Okay, and then finally, part F. Approximately 1 centimeter cubed of dilute nitric acid was added, and then they added barium nitrate, BaNO3. So, of course, anytime you see Ba, okay, and you have SO42 minus, the Ba will react with the SO42 minus to produce a white precipitate. So you see how easily everything became just by memorizing, by understanding the flame test and everything. This chapter is all about memorizing and understanding in some way. So thank you guys for watching. I hope you enjoyed chapter 2 solubility notes, and if you guys have any questions, please do comment.